In this video, we will continue our investigation into the convergence and divergence of series. Specifically, we will look at two new tests, first of which is the comparison test. The comparison test states that if you have two series where you're summing up the A sub n and the B sub n, which are all positive terms, so that's a very important observation, and additionally, the A sub n is always smaller than or equal to the B sub n. Then we have the following two conclusions. If the bigger series converges, because remember the B sub n is bigger, if the bigger series converges, anything smaller will converge as well. If the smaller thing diverges, then anything larger will diverge. And that's really the intuition. As long as you have series with positive terms, if the bigger thing converges, so does the smaller one. If the smaller one diverges, then so does anything bigger than it. Now, as the name indicates with the comparison test, you're typically going to have to come up with a series which you can compare with. And for now, there's really two types of series that we can compare with. One of them, which is hopefully still very familiar to us, the geometric series. And recall for geometric series, that is a series of the form the sum from n equals 1 to infinity of AR to the n minus 1. And at this point, what we're really going to be most interested in is just, does the series converge or does it diverge? Not what its sum would be. It turns out determining the sum of the series is typically a much harder question. So in terms of a geometric series, we recall that this series converges when the absolute value of r is less than 1, and diverges when the absolute value of r is bigger than or equal to 1. A second type of series that we can compare with is going to be something called a P series. A P series is a series of the form the sum from n equals 1 to infinity of 1 over n raised to the pth power. And if you go back to our previous examples involving the integral test, we went over two such examples. And for a P series, the P series will converge specifically when P is larger than 1 and will diverge when P is less than or equal to 1. Now in terms of the divergence case, this borderline value of 1, the sum from n equals 1 to infinity of 1 over n, so this is corresponding to P equals 1, is something which is called the harmonic series, and it appears frequently enough that it has its own name. And the harmonic series diverges because it's a P series with P equals to 1. And in terms of the convergence or divergence of the P series, this follows directly from using the integral test. So let's look at an example of how the comparison test can be applied. Let's determine whether the given series is convergent or divergent. So looking at what we are summing up, 5 over 2n squared plus 4n plus 3. So recall, to use the comparison test, we need our series to have all positive terms. So these terms will certainly all be positive. But we'll wait a moment to write down where that 0 is going to go, on which side of the inequality. So to use a comparison test, we need to think intuitively about what we would like to compare to. And my intuition here is to really look at kind of the biggest terms in the top and the bottom. Those are going to determine what's going to happen with the series. So the biggest term in the top is the only thing there, the 5, and in the bottom it's 2n squared. Now note what else we have in the bottom. We're adding 4n, we're adding 3. And a bit of intuition, dividing by something bigger gives you something smaller. So if we were to compare this with just those biggest terms in the top and the bottom, on the left, since we're adding a 4n and we're adding a 3 in the bottom, we're dividing by something bigger and we get something smaller. Additionally, these are all positive quantities. So now looking at what we have and comparing above. We know if the bigger thing converges, that's what we're comparing to here, then so does the smaller thing. So let's make an observation. If we have the sum from n equals 1 to infinity of 5 over 2n squared, we can think of 5/2 as a constant, which we pull out. So the sum from n equals 1 to infinity of 1 over n squared. And this leaves us in an ideal situation. The series that remains is a P series. And furthermore, the value of P is 2. So this is a convergent P series. And we should always indicate why. The reason here is it's a p-value of 2, and 2 is bigger than 1. And now we can make our conclusion. The series which we've compared it with is bigger and convergent. So that means anything smaller is also going to converge. So our conclusion is, by the comparison test, and we can always use just CT for comparison test, it follows that the series we are interested in, the sum from n equals 1 to infinity, 5 over 2n squared plus 4n plus 3, converges. And as mentioned previously, we should always include a conclusion which shows the original series, whether it converges or diverges, and by what test we are using. Well, let's investigate another example. So given the series here, can we determine whether this series converges or diverges? So let's approach this with the exact same intuition we had before. So what we are summing up is 1 over the square root of n squared plus 19n. And recall, in order to use the comparison test, we do need all positive terms, but we certainly have that here. Now, what do we want to compare it to? We want to take the biggest quantity in the top and the biggest quantity in the bottom. And that's just some intuition. It's not always true, but usually it's a good indicator. So if we compare this with 1 over the square root of n squared, and note, 1 over the square root of n squared is really 1 over n because n is positive. Dividing by something bigger gives you something smaller. So because we have that plus 19n in the bottom, it's smaller on the left than the right. And these are all positive quantities. So note, if we think about the sum from n equals 1 to infinity of 1 over n, this is the divergent harmonic series. That is a P series with P equals 1. But it diverges. And in this case, the comparison test does not help us. The reason being is if a bigger quantity diverges, we don't know anything about a smaller quantity. We can only use the comparison test for divergence if we know a smaller thing diverges than anything bigger than it diverges. So what do we do when we want to apply the comparison test, but the inequality is not going in the right direction? We use something called the limit comparison test. The limit comparison test tells us the following. If once again we have two series where the terms are all positive, and now the difference, if we take the limit as n approaches infinity of the quotient an over bn, and we get back some number L which is positive, so bigger than 0, and finite, less than infinity, then both of the series will converge or both of the series will diverge. So let's see how we can use this with our previous example. So once again, the intuition is that we wanted to use the comparison test and we already did the work and we saw it doesn't apply. But what we said is that this thing is going to hopefully behave much like looking at just the biggest terms in the top and the bottom. So 1 divided by the square root of n squared. So we will apply the limit comparison test, and we will abbreviate that with LCT using a sub n being the given series, the one we are interested in, and b sub n being this one we would like to compare with. 1 over the square root of n squared, which is 1 over n. So for the limit comparison test, we need to evaluate what is the limit as n approaches infinity of a sub n over b sub n. So that would be the limit as n approaches infinity of 1 divided by the square root of n squared plus 19n divided by 1 over the square root of n squared. So multiplying by the reciprocal in the bottom and combining into a single square root, so a bit of algebra, this would be the limit as n approaches infinity of the square root of n squared divided by n squared plus 19n. And then recalling that we can take a limit and plug it inside a continuous function. We can put that limit inside the square root, and we can write this as the square root of the limit as n approaches infinity of n squared over n squared plus 19n, degree 2 over degree 2, so we divide the leading coefficients, and the value of this limit is 1. And I'm going to put a check. Note 1 is our L value, which is between 0 and infinity. It's a positive finite number. So that means both of these series converge or both of these series diverge. Looking at our comparison series, 1 over n, it diverges, therefore so does the original. But recall, we need a conclusion. So since the sum from n equals 1 to infinity of 1 over n diverges, and note P series with P equals 1, which is why it diverges, the limit comparison test implies that the series we are interested in, the sum from n equals 1 to infinity of 1 over the square root of n squared plus 19n, also diverges. And note that it is absolutely imperative that you include some type of conclusion. And note the important characteristics. You need to rewrite down the original series so we know which one we're talking about. Mention whether it converges or diverges in the specific test that's indicating why that is the case. The intuition in terms of when we would like to apply the limit comparison test is exactly what we've seen here. We're in the situation where we would like to apply the comparison test, but the inequality will not allow us to do so.